This video we are going to discuss about the topic given in computer organization and architecture. The first one is about basic processing unit. In computers we have 5 basic units like input device, that is input unit, output unit, then memory unit, control unit, arithmetic and logical unit. There are 5 basic units we have in the computers. Then the CPU includes control unit and arithmetic and logical unit. Here, the processor fetches one instruction at a time and performs the specified operation. If you want to execute any instruction, we have to go for executing the following steps like fetch, decode and execute. Fetch, that includes fetching the instruction from the specified memory location. Decode determines the opcode and operands, and execution is nothing but running the instructions. Then executing an instruction that involves fetching the instruction fetch phase. Then for fetching instruction, first the CPU has to refer the program counter. What is program counter? It's a register which includes the content of the next instruction is going to be executed. The address of the next instruction going to be executed is in PC program counter. The IR contains the address which is currently being executed. So fetching instruction involves refer the PC, address the next instruction, then go to that memory location, fetch that instruction, that load that instruction into this IR. After this you have to add this 4, that is it's a one instruction length. Add this PC plus PC4 will give you the address the next instruction. Then in case of branch instruction, the target will be loaded here. So here data path includes collection of functional units such as ALU or multipliers that perform data processing operations. So execution of instruction includes two basic operations, fetch phase and execute phase. Fetch phase, the instruction is fetched from the memory and loaded into the instruction register IR, and execute phase, we are going to execute that instruction. In this case, how we are going to communicate with memory? We have two registers, MDR and MER. The MDR here, memory data register, whatever data is going to be read from memory or write into the memory, it should be loaded into this MDR. Which location we are going to access from memory, that address will be loaded into this MER. Here we can perform only read and write operation in memory. So here reading or writing, whatever may be the operation, the location which you want to access is loaded into MDR. The content you want to write or read from memory will be loaded into this MDR. So only with these two registers we can communicate with that memory. The CPU can communicate with memory only using these two registers, MDR and MER. Here control lines, this is for generating the control signals. The signals will give the information what will be performed at what time. Okay, this will be generated using this hardware signal or microprogram control signals. Then R0 to Rn minus 1, that is we have n number of general purpose registers for performing some mathematical calculations. Then we have temporary registers like temp, y, z. So CPU have this all the registers. The general bus organization, that is how these registers or other units, the computers are connected together using a single bus. Bus is nothing but group of wires that connects the components of the computers. Here the PC, the program counter, is a register that holds the address of the next instructions is going to be executed. MER is a register, memory address register. In memory, which location you want to access, that address will be loaded either for read or writing purpose. Then here MDR is a memory data register. Whatever content will be read from this memory is loaded, or whatever content is going to be written into the memory will be loaded into this MDR. Here we have Y register, temporary registers. Then we have a multiplexer for selecting this Y, either Y or 4. Then it's arithmetic and logical unit for performing this ALU operations. Then Z register, temporary register, we have n number of control general purpose registers, R0 to Rn-1, temporary register, IR is instruction register. It's which instruction is currently being executed. that instruction is available in that, then that information given to your control unit. Here maybe either you are using this hardware control or microprogram control for generating the control signal. So entire unit is, it's a heart of your computer system. Then this is going to generate the signal. Based on that, the operation will be performed. The read or write or what operation, the addition, whatever may be that. Everything is controlled using this control unit. So performing an arithmetic operation or logical operation, how do you perform? You want to add the content of R1 and R2 and store it in this R3. In this case, how do you generate the signals, control signals? First, we have to get the value of R1 out, then R2 out, add these two, store it in R3. Here, this can be performed using this signal. Actually, each register we have a in and out signals. Okay, if it's going to connect to single bus, then we have only one in and out signals. Here, this MDR register is connected with CPU as well as this memory unit. So here it's having this in, out for connecting with that CPU, and here this is for connecting with that external part, that's memory. So it's called E. So here you want to perform addition of R1, R2 and R, store the result in R3 means first get the value of R1 out. Using the signal, get the value of R1, store this in Y in. Signal will be given for storing the R1 content into this Y register. Then get the value of R2 using this R2 out signal and select the Y for adding. Give the add signal, result will be stored in Z. Then get the Z value out and store it in this R3. This way we have to generate the control signals. These are control signals. Based on that, the operations are going to be performed. Here we have this MFC signal, memory function completed signal. Once the read or write operation is completed, this will be given to your CPU. For see, the speed of the memory is really less when compared to that CPU. Okay, so the CPU has to wait till the memory function is completed. Once it's been completed, either read or write operation, it is giving this MFC signal. Okay, then for writing, so it has to wait for this MFC signal, writing or reading the purpose. It has to wait for WMFC signal. Here we have a code for the control signal generated for performing this operation move R1 of R2. Here R1 is the indirect addressing. Indirect in the sense R1 is having a address of some operand. Okay, so here go to this R1, get the address and load the see the memory, get that operand value. Again move that content into this R2. How do you get this one? R1 out, get the value of R1 out, store this MAR. Because it's the brackets are not given means you can directly get the value of R1, but it's indirect addressing in the sense address of that operand is stored in the R1. So we have to refer this in memory. So store the address in MAR in, give the read signal, load the value into this MDR in, then once wait for the memory function completed and get the value of out MDR and store this in R2. This is the way we are generating the control signals for performing this task. So execution of complete instruction. Okay, you want to execute complete instruction. There are 7 steps. It's for normal steps. In case of any branch instruction, this will be reduced. Okay. Here first what happens, you are going to refer the PC value. It contains address of the next instruction. So get the PC value using the signal PC out. Store the value in MER. Okay. Because the PC address is stored in the instructions are stored in the memory. Then PC is having the address of the next instruction. So get the next instruction from the memory. For that, load the PC value to MER. Give read signal. Then here select for and add is for updating the PC with next instruction address. Once it's been taken, then you have to go for PC is equal to PC plus 4. So select 4 and add the PC with 4. Store the result in Z. Again get the Z value, update the new PC value. This is we are performing in second step. Okay, and also stored in Y. Once the MFC is completed in the sense, the data is whatever data you want to read in that address, that will be available in this MDR. So get the MDR value stored in this IR. So whatever you have in this MDR, the instruction is loaded into instruction register. Now check what is the instruction. Okay, assume the instructions like the instruction may be here get the value of R3, store the value of this R3 into this MAR, read, get the value of R1, W in, here MDR out, S select Y. So here we are performing the operation of I think move R3 comma the indirect addressing comma R1 operation we are performing. We just go ahead, wait for the memory function completed, get the value of MDR and this select Y add operations, move the value into this R1. Okay, so here this is the way we are performing the task. Here the instructions given like R3 add R3 comma R1. This is the instruction given. This is a control signal generated for the given instruction. So here each register we have this in and out registers. It's called signal diagram. When you want to go for any branch instructions, then we have only 5 steps, basic steps. First 2 steps for updating the PC and get the instruction. So first 3, get the PC, refer PC, load this in MAR, read, update the PC and load the data and the instruction into this IR. If you see it's a branch instruction, then go for calculating target address using offset field. Okay, this is the way we are executing, we are generating the signals for branch instructions. So here conditional branch, we have some conditional codes. The 1-bit register, it's having information. Maybe carry flag, if you're adding getting carry flag, this will be set 0, the result may be 0 or any sign or overflow. We have different conditional code registers. This is single path bus organization data bus. Okay, we discussed. Then if it's a drawback is we have a single connection. So instead you can go for multiple bus. Okay, to avoid this delay. So you can go for this multiple bus. Here we have bus A, B, C. Here this is all connector. And the components are connected with different buses. Okay. If you want to execute this add R4, R5 and R6, how do you generate the control signal? Get the PC value. R is equal to B in the sense, get the PC using this B bus. Because PC is connected to the B bus, so this is R is equal to B. MAR in, read, increment the PC. Instead of selecting 4, adding this PC plus 4, you have a simple signal like increment 4, increment PC in the sense it will be like PC is equal to PC plus 4. WMFC is completed, then get the MDR out. Here the MDR out using this either by B bus or A bus. Here you are mentioning like B means the out will be taken using this B bus. Okay, this is the way we can go for multiple bus organization. So far we are discussing about these are all the control signals that has to be generated for executing the instructions. How do you generate the control signals? There are 2 ways. Hardware control using circuit, or we can go for some micro programs. First one is about hardware control. Hardware control, here this to execute the instruction, the processor has generated some control signals, right? The hardware or micro program. In this case, hardware control using some circuits. This example, you want to perform R3, R1. These are the steps we discussed. Then here we have the step counter, instruction register, conditional code, flags, and MFC request. So basic control unit organization of hardware controllers, we have clock signal, then control step counter, instruction register, decoder, external inputs and conditional codes. Based on the inputs from this counter, instruction, external input and conditional code, the respective control signal will be generated. Okay, based on that the operation will be performed in D time. You can see this, we have a step counter at what time this is going to be generated, then what kind of instructions it's going to give, add, sub, mul, like that kind of instruction in D time. So here this T1, for example, T time, what are the instructions are going to be performed. For example, you have a instruction. So in the instruction, here when and all you are going to use this Z in. This Z in means you are going to load something into the Z register. So when the T1 time, T6 you are going to use it for addition operation, if it's a branch instruction, P4 time this is going to be used. Like that we have a setup. We are defining the architecture. In case of end of your program execution, the end signal will be called at the time of, if it's add signal T7 it is going to be called, it's a branch instruction T5. Like that we have a we are designing the circuit. In microprogram control unit, here we are going to have a binary control variables. It's are stored in the memory. Then the particular control word is going to be taken for generating the control signals. Here the control signals is going to be generated by this multiplexer, decoders and arithmetic logic units. Then the micro operations are nothing but binary variables. It's called control variables. Here the control variables in the form of zeros and ones, nothing but control word. Then memory contains control word. The control word is stored in the control memory. If you want to generate any control signals, then execute the micro operations. It's a sequence of micro instructions, nothing but micro program. Here hardware control, this is a simple circuit we have, but micro program we have the instruction code, we have this next address we have to generate. It's nothing but control address register. The memory is having all the micro instructions. Then control data register, get refer which micro instruction you want to execute for generating the control signal. That is address will be loaded here. It's that one. Okay. Then give it the decoding for generating control signals. Looping is also given. Okay, this way we are generating the control signals in microprogram unit. So the specific address will be given to the control memory, micro instruction will be fetched. So the same thing what we discussed for the normal instruction, here we have to go for fetching the instruction from the control memory, then find the address, fetch the particular micro instruction, execute it, generate the control signals. So here the external input, generate the address, control address register, fetch that, access at particular location, get it and execute it. So here we have this control memory address register, decoder, control memory, fetch that micro instruction, then generate the